As developers, as architects, we actually have an incredibly important role in today's world. A world in which, let's face it, is completely run by technology. Almost every part of our day-to-day life is governed in some way by software. And the users we build for have got a lot of different things that they want. All users, of course, want things to be fast. Users are never happy, things could always be faster, be quicker. And actually, the speed of your software you build can have a direct impact on people's job satisfaction and their productivity. For anybody who's ever used Salesforce with any gusto, you'll know exactly what I mean. But users, as well as wanting things to be fast, they also want things to be safe. Safe both for the people using the software, but also safe for all of you as developers. Who's ever had a piece of software fail that they've built because of something out of their control? A server's failed unexpectedly. You've tried to upgrade a Kubernetes cluster and it's gone wrong. Like, these things happen, but you can't directly control them. And as well as that, we also want things to be sustainable. Both sustainable from a cost perspective, but also sustainable from an environmental perspective. And I believe we have a responsibility as people working in software to make things as sustainable as possible. And as the great Oprah Winfrey said, you can have it all, you just can't have it all at once. These three different things that you're trying to work with pull you in three different directions. They're quite conflicting. How do you build something that is fast and safe, but also sustainable? And that's what you're going to learn about in this talk, how serverless compute and the Rust programming language can work together to help you build systems that are faster, safer, and sustainable. Now, I think it's also important I tell you what this talk isn't. This talk isn't going to be a deep dive into the internals of Rust, into the programming language. Don't expect slides and slides and slides of application code. This talk's more about what you do after you've written the code, the kind of boring day two stuff. So I'm James Eastham. I'm a developer advocate at Datadog. And I actually want to start by being really honest with all of you. I've worked in frontline support. I've been a DBA with SQL Server. I've worked at AWS. I've built serverless systems. I've built server-full systems. I'm really new to the world of Rust. So one thing I ask of all of you is that if you see anything in my code samples, anything with any of my content you might engage with online, and you think this guy has no idea what he's doing with Rust, please point it out, let me know, because I'd love to learn from you as much as you learn from me. And to make this really real for a moment, I want you to forget everything you know about your day job. The hundreds of Jira tickets you've got in the backlog, forget your day job, because for the rest of this talk, you're all now developers for a completely fictional pizza delivery company called Plant-Based Pizza, the country's #1 Roman-style pizza delivery company. Now, I realise I'm doing this talk in Italy. This could be a really contentious topic. Please just bear with me if you don't think Roman-style pizza is the best. And this is you. You love your job. Your job's got that perfect balance of things just about being difficult enough that they're engaging, but you're comfortable. You know what you're doing. You bounce into work every day. Things are good, apart from when you're on call, of course. Things are good. And this is Helen. Helen's a principal engineer at Plant-Based Pizza. She's also your line manager, and she's one of the best developers you've ever worked with. She's got this perfect balance between being really analytical and really understanding things, as well as a lot of experience building large-scale distributed systems. And she comes to you with a problem. She says, you've got to build a new service. The company wants to start supporting loyalty points. So when people come back and start buying more pizzas, they can collect loyalty points and hopefully get some free pizza at some point. But she gives you some constraints you need to work with. The first constraint is you're going to be the only person working on the project. You can't rely on any other internal infrastructure teams, any other developers. This project is you and you only. The system you build also needs to be fast. This isn't on the core user flow through the application, so it needs to not add additional latency to the application. And the company's also got ambitious cost and sustainability goals. So as well as both of them things, you also need it to make it sustainable. And one more thing, actually, you need to deliver it inside a week. Stressful, right? You feel that fear already coming over you. Frankly, you try everything you can to stay in your comfort zone. You start muttering something about it depends. You remember something that Oprah Winfrey once said. No movement. You still need to do it. So you decide to bring out the big guns. You decide to say, it depends. Smugly, of course, it depends. You can't have all them things. Surely things can't be fast, safe, and sustainable. But you still need to build it. So let's go off and let's try and build this system. And at a high level, this is the existing system you've got to work with. There's some kind of order processing system. It's publishing events onto a Kafka topic. You need to consume them events, and that's when you know you need to add loyalty points to a customer's account. You also need some kind of web interface for the front end to be able to get current users' points, and also for them to spend points to get a free pizza. So you decide at a really high level, this is what you need to build. And really, there's three kind of primary components in the system that you need to build. You need some kind of background service, something running in the background that's going to poll the Kafka topic, get the order completed events, and then you're going to persist a user's loyalty account information somewhere. And then, of course, you need some kind of web app that's going to allow the front end to retrieve this information. And you need to do all of that in a way that's sustainable, fast, and safe. So you decide to start picking these things off one by one. Remember, you're a one-person team on the project, so you want this application to be safe. Safe from a security perspective, of course, but also safe from an operational perspective. You don't want to be spending all your time worrying about managing servers, worrying about dealing with all that operational stuff. You want to just write code. You're a developer. And when you really boil it down, there's two types of safety you need to deal with. There's application safety and there's infrastructure safety. Application safety is the stuff that you really have control over. Dealing with edge cases in your code, error handling, type safety, memory management. They're the things that you can control inside your application code. And then you've got infrastructure safety. Infrastructure safety comes from how you choose to deploy that application. How does the compute you choose to use affect your uptime, affect your resilience, affect your latency? So you decide to start with the thing that you've got control over, application safety, which brings us nicely onto Rust and the adorable Ferris the crab. Now, a really quick side note, my girlfriend works in strength and conditioning, so she knows nothing about tech. She loves Rust because of Ferris. She's got a little sticker on her laptop and everything. It's hilarious. And you've been learning Rust for a little while now. You're reasonably proficient in the language. This seems like a perfect use case for what you need to build. It's fast, it's safe, and it can do work with reasonably little resource consumption. You think to yourself, in all honesty, that Ferris should really be wearing a cape, actually. Now, it's not just you that thinks Rust is a safe language. Numerous security services from all over the world jointly published a paper talking about how we should all be using memory-safe programming languages. Now, Rust is one of the strictest low-level languages as far as memory safety goes, whilst also giving you some really nice zero-cost abstractions on top of that. Now, of course, that's specifically focused on memory safety. But if you caught Daniel's talk yesterday and Ed's talk earlier today, you'll have seen some of the features of the Rust language that make you write safer application code. The way that functions can return results that have an OK value and an error value. And that error could be an enum, and if you don't handle one of the options of the enum, one of the edge cases, your code won't compile. So there's a lot of features in the language. There's an entire talk about the features of the language that help you write safer code. But that's not what we're focused on today. You're focused on how you run this application. So this is what you end up with. You've got your application code written, you've got a web API using the Eastham framework, you're using Postgres as your database provider, and you've got some kind of background service that's using the RD Kafka crate to consume messages from the Kafka topic. Which brings us on to this topic of infrastructure safety. If you're anything like me, you really just want to write code. You don't really want to care how that code runs. I've spent longer than I would like to admit in my career deploying .NET applications to Windows servers. I've even once accidentally turned off a production Windows server thinking it was my local machine. I shut my laptop down, walked out and left for the day, and then 10 minutes later got a phone call because I was remote desktop. Windows didn't make these things easy. And remember, you're a one-person team. You've got some apps that you just need to run, and you don't really want to worry about anything else. Which brings you nicely onto the world of serverless. How you can just take your application code, pick it up and drop it into a serverless compute, and, well, the cloud provider handles the rest. That's the promise, at least. There's a slight challenge here, though. There's a rule inside plant-based pizza that actually you should try and avoid managed services as much as possible. Someone once muttered something about vendor lock-in, and now everyone's panicking about this thing called vendor lock-in. We'll come back to that in a minute. Serverless has also become a bit of a lauded term in recent times. It was kind of co-opted by marketing teams, and lots of things said they were serverless that probably weren't. So the way to think about serverless is not as being serverless or not serverless. Serverless is a spectrum. It is not a binary choice. You can choose to be more or less serverless. From a compute perspective, you could choose to run your application as serverless as possible, which means you have very little, if not zero, operational overhead. The trade-off you make if you do that is if you lose infrastructure flexibility. So you get some really opinionated compute. You lose control of the underlying infrastructure. There's another interesting dimension to think about this, though. That's the cost dimension. If you look at the line item cost of serverless compute, it is more expensive than running raw virtual machines. But when you consider the human cost of managing that infrastructure, if you choose to run a virtual machine, you need to pay somebody to run that virtual machine. If you choose serverless compute, you're paying the cloud provider to do that. And cloud providers are very good at running infrastructure. So to make this really real for a minute, let's consider the compute options you have when it comes to serverless technologies. You've got the truest definition of serverless on the kind of far right of the spectrum. Things like Lambda, things like Azure Functions, like Google Cloud Run, and Cloudflare Workers. These are the truest definition, things that scale up when there's work to do, scale all the way down to zero when there's no work to do, and you only pay for your code exactly when it's running. The truest definition of serverless. But as you start to move down this spectrum, you start to move through some other interesting technologies. Things like Azure Container Apps and Amazon ECS. Services that are container orchestrators, but allow you to deploy applications without worrying about what's going on under the hood. Azure Container Apps is built on top of Kubernetes, but you can simply just give it a container image, some CPU and some memory, and Azure will manage everything else. Of course, as you start to move down this spectrum, you start to get into things like Kubernetes, actually running Kubernetes. Maybe you use a managed Kubernetes service where the cloud provider operates the control plane for you, but you've still got to worry about upgrading the cluster, installing things on that cluster, writing thousands of lines of YAML. You've got to do all them things yourself. And then, of course, at the bottom end of the spectrum, you've got actual virtual machines, or even, as seems to be coming back into fashion, running physical machines in physical data centers again. And remember, there's no right or wrong place to be on this spectrum. You can just choose where to sit based on what your application needs. If you need some really specific GPUs, some really specific infrastructure, you're probably going to need to sit further left. But for the majority of business applications that at least I've worked with, you want to stay as far right on this spectrum as possible. Your users do not care how well you can operate and scale a Kubernetes cluster. They care about the application working. And I want to say a really quick word, actually, on Cloudflare Workers. If you haven't heard, Cloudflare, yeah, those DNS and security people, they've actually got an entire cloud platform now. Now, I'm not affiliated in any way with Cloudflare. It's just a really powerful tool. The developer experience is fantastic. You can deploy Rust to Cloudflare Workers, albeit you have to compile your code to WebAssembly, which is its own talk again. But it's a really good developer experience. So if you want to build some things, POC, some maybe sample apps, Cloudflare is a really good place to do that, and it's really low cost. But moving on, this serverless spectrum you look at doesn't just apply to compute. It also applies to databases. You need a Postgres database as your persistent store. Now, you could choose to run Postgres on a virtual machine. Do you really want to be doing that in 2024? That's a call for you to make, of course. But remember, you're a one-person team. You don't really want to be thinking about infrastructure. You could refactor your code to use a native database service, something like DynamoDB, like Cosmos DB, like Firestore. But coming back to that conversation around lock-in, actually using proprietary database services where you have to use a specific SDK, a specific data model, that is more of a form of lock-in than the compute you choose to use. Yet everyone seems to focus on the compute. So you don't really want to do that. You could, of course, use a managed service that all the cloud providers give you to run Postgres, or you could use one of the third parties that are starting to pop up. Companies like CockroachDB, companies like NeonDB, companies that are starting to give you really low operational overhead. That's not a real word. Operationally light Postgres. There we go. And I want to give a quick shout out to Neon. Again, I'm not affiliated anyway. It's just a really, really cool technology if you need Postgres. This is fully serverless Postgres. The database will scale up when there's work to do. It will scale to zero. It can cold start in about 10 milliseconds or 20 milliseconds. Of course, your compute scales to zero. Your storage doesn't scale to zero. That wouldn't be ideal. But it's a really powerful thing. You can branch your database. You can do all sorts of really cool stuff. So I'd really recommend checking out Neon if you need Postgres for anything new. And as you may expect, this serverless spectrum applies to other layers of your app as well, your messaging layers, your storage layers. You've got these choices at all these different levels. What you should take away is that thinking serverless first is just about reducing your operational overhead as much as possible. So you decide to build with serverless. You decide to take the risk. You decide to ignore the rules you've got internally. This is kind of worth it with the value proposition you think. And you go off and build. At the moment, you've got these two Rust applications that you need to deploy. One polling the Kafka cluster, one serving the web traffic. And you have a look at the different options you have on AWS for running containers. Plant-based pizza is all in on AWS. That QR code you can see in the corner is to a GitHub repository that has this same application deployed to various different cloud providers. If you want to go and have a look at that, the QR code is there again at the end. So when you look at how you want to deploy your application now, you know that you don't really want to use EC2. You don't really want to worry about managing servers. And you also think, well, Lambda's this reactive style of compute. Lambda's got its own programming model, so surely Lambda's not an option, right? Hold that thought. Which gives you, from a container orchestrator perspective, Kubernetes or ECS. Now, Kubernetes has its benefits, it has its merits, but there is overhead to running Kubernetes, right? You're still a one-person team, so you don't really want to use Kubernetes, which leaves you with Amazon ECS and Fargate. If you're not familiar, ECS just allows you to create a cluster. Clusters are zero cost, they don't cost you anything. You can define a service inside that cluster, and that service can run your app with two different compute options, one being EC2, virtual machines, one being Fargate. Fargate just allows you to say, here's some CPU, here's some memory, I want you to run my application with that configuration. The lowest memory you can allocate to a Fargate task is 512 megabytes. And of course, to run your Rust application as a container, you're going to need a Docker file. When building serverless apps, you want to try and keep your package size as small as possible. When things are being dynamically scaled up and scaled down, the smaller you can make the package of application, the faster things can be pulled, the faster things can be started up. Now, there's a lot going on in this Docker file. I'm not going to dive through it in a lot of detail. Just know that it's using Alpine as the base OS, and it supports multi-architecture builds. So you can build a container image that will support both x86 and ARM64. If you want to dive deeper on that, there's a really good blog post that one of my colleagues, Scott, has written, linked in the corner, for how to set up Docker files for multi-architecture targeting in Rust. It's a really good write-up. So here's where you've ended up. You've got your two Rust applications packaged as container images, one polling the Kafka cluster, one running the web app. You've got Neon for your Postgres database. Everyone's happy. We're done. Celebrate, right? If I had a mic, I'd drop it and walk out. Easy as that, you think. You can go home, you can wait for the promotions to start coming in, happy days. You've just delivered a complete new service in less than a week, and you're running it with basically zero operational overhead. And then Helen comes along again. This is all well and good, she says, but how do you actually know? How do you actually know that your application is fast and safe? How do you actually understand what is happening inside your application? You might tell me that it's serverless and it's fast and it's safe, but is it? And this is where observability becomes really important. Being able to understand how your application is performing is, well, quite important when you choose where you're going to run that application. And observability is simply the ability to understand the internal state of your system by looking at its external outputs. Now, to look at external outputs, of course, you're going to need some external outputs coming out of your application. And thankfully in Rust, this is made really easy. There's the whole tracing ecosystem. Tracing is a set of crates that make it really easy to collect structured diagnostics from your running application. And that's really great. It's really easy to use inside your application code, but actually open telemetry is becoming a bit of a standard nowadays for observing applications. Now, thankfully, there's a really useful crate in the tracing ecosystem called tracing-OpenTelemetry, which acts as a bridge between the tracing crate and the OpenTelemetry SDK for Rust. Which means when your application starts up, you simply need to configure a gRPC exporter to send your telemetry data to an OpenTelemetry endpoint. Here you're using Tonic, and you're passing in that OpenTelemetry endpoint as an environment variable. You then need to set up your OpenTelemetry tracer. You can set some default service names. You can configure how the exporting works. And then this last line of code here is the important one. This is what adds the OpenTelemetry tracer to the the layers in the tracing crate, which means whenever you instrument your code with the tracing crate, that information will be sent via the gRPC exporter to an OpenTelemetry compatible endpoint. And then, of course, when your application starts up, you just need to make sure that you configure this instrumentation. You can move this into some kind of utility function, and you can call that in the main function for all your apps. Once you have all this set up, it allows you to really easily start to instrument your application. You can add macros to your functions to instrument the application, to generate custom spans for that individual function's runtime. So this is the function that gets called by the Axon web framework whenever someone's trying to retrieve loyalty information. You can use this to understand the performance of that API endpoint. And there's some really nice utilities that this tracing crate has as well. It allows you to, the crate will automatically annotate your traces with the value of the variables you pass to the function. So here you're passing self and you're passing a customer ID. Now, of course, you probably don't want to annotate the entirety of self to a trace. In a lot of cases, that probably wouldn't even work. So you can skip properties. This can also be useful for PII information to allow you to skip certain properties that you might not want to store in your observability system. But we do want to store the customer ID. Maybe we want to keep track of which customer these given requests are for. Once you get into your observability system, then you can start to understand the requests that are flowing through your system. You can see the individual requests as they flow through. And then you can start to sort these requests by the slowest. Which requests are affecting my latency the most? And you can start to dive even deeper into them and understand exactly what is happening during these slow requests. And maybe even do smart things, start looking at your requests by customer, start looking at your requests by order number, by the number of lines on an order, all these different things you can use to query your system. Now, all this is really nice to have, of course, but fundamentally what you're trying to do is to prove that your system is performant when it's running on serverless compute. So when you pull all this telemetry together, you can start to generate performance numbers. So for this Rust web app running on Fargate, the maximum latency of the API is 325 milliseconds. Now, I know in the context of Rust, that could be considered slow, but when you've got a web app querying a Postgres database and returning results, 300 milliseconds is pretty good. And your P50 is 100 milliseconds. It's pretty good. So now it must be time to celebrate, right? We've proved that this app is performant enough for our users' needs. But there's a problem. You're getting to the real challenge of the situation now, because what you've got here is two long-running container images. They're running 24 hours a day, 7 days a week. They've got 512 megabytes of memory assigned. That doesn't feel particularly sustainable, does it? So what about sustainability? This is the big one. There's plenty of articles out there, hundreds, thousands of articles, YouTube videos on how to make software safer, how to make software faster. There's not many on how to make software more sustainable. How do you both save money and save resources without sacrificing one of the other two? So you revisit your current system. You've got your user-facing web application that's quite happily chugging along, serving requests, and you're serving thousands of requests with a reasonably small number of running container images because Rust. But you've got this background service. This background service is only doing work when there's messages on the topic. But other than that, it's just sat there running 24 hours a day, 7 days a week, not actually doing a lot. And when you go and actually look at the resource consumption of this service, even under load, it's only using about 6% of the available CPU and about 1% of the available memory. So you think, well, this seems like a perfect place to optimize. Which brings you to the truest definition of serverless. Services like Lambda, services like Azure Functions, where reactivity is their superpower. Services that will scale up when there's work to do, scale down when there's no work to be done, and you only pay and use the resources when your code is actually running. You can hook your code up to some kind of event source. That event source could be an API, it could be a queue, it could be a bus, it could even be a Kafka topic. And when you think about functions as a service environments like Lambda, they're fundamentally different ways of thinking about running applications. Instead of having a single running instance of your app where you've got multiple requests all being handled by that same running instance, serverless environments typically restrict the concurrency that your application has. So Lambda, each environment that's running, will only process one request at any one time. Cloud Run, Google Cloud Run, allows you to configure that concurrency. How many requests do you want your app to be able to handle at any one time? Which in practice makes your application look a little bit something like this. You've got lots and lots of running instances of your application, all handling a single request at a time. And when you think about this as a model, it really starts to look similar to how you might run IoT devices or edge compute. Compute where you're pretty typically heavily resource constrained, and you've got some application code that you need to run in a reasonably resource constrained environment. Individual resource constrained environments where you want performance to be good sounds like a perfect place to bring back our crab-shaped superhero again. This all sounds great, doesn't it? You've got this perfect place that seems to align really well with this reactive style of compute, and you've got an application that needs to react to messages. But when you actually look at your application code isn't really suitable for this. Your application code at the minute running inside a container is consuming messages from the Kafka topic. Again, this uses the RD Kafka crate. You set up a consumer where you configure a topic to consume from, and then you call this receive function. Your code's going to wait at this point until the message is received, and once it's received, it's actually going to call into your application code. So you've got this long-running process, this long pol, if you will. Once you're actually processing an individual message, all you really need to do is to deserialize the contents of the message. You're going to pull that payload out of the message on Kafka, deserialize that to a type relevant to your application, and then just call into your business logic. Remember, the way you've set your code up separates these things. And then once all that's done, you need to commit the message back to Kafka to move along where you're up to in that given partition. This doesn't feel particularly ready to run in Lambda, right? So to understand what you need to do to get this ready to run in Lambda, let's first understand more deeply how Lambda works. And other functions as a service environments work in a similar way, not identical. So when a request comes into Lambda, the execution lifecycle is started. An execution environment gets created, your code gets downloaded, the runtime is started up, the runtime is initialized, and then your application code runs. The request is actually handled. That initialization phase is what's known as a cold start. And if you're familiar with serverless, you've probably seen people bashing cold starts all over the internet. What actually happens behind the scenes, when your first request comes into your Lambda function, that execution lifecycle is started. So the application started up, the request is handled, and if a second request comes in whilst that first request is still in process, another execution environment is created, which sounds horribly inefficient, right? Then if a third request comes in, that third request, well, there's that first environment that's been created that's still in use. These environments hang around for a little while. So that third request will be handled by that same first environment, which is what's known as a warm start. That environment's being reused. So because these environments are reused a little bit, there's some patterns and practices you can use in your application code to make things more efficient. When Lambda runs your Rust application, all it's going to do is download the binary, the compiled binary, and it's just going to run that code, which means you're still going to have a main function, like you would in every Rust application. In your main function, you're going to want to configure anything that can be reused with subsequent invokes. Setting up database connections, downloading secrets, setting up your telemetry, all that thing that can be reused over and over again, which actually is much the same as you would do if you were building a web app or a web API. You'd configure all the things up front, and then you'd pass them as to the individual requests to be used. This last line of code here is what's specific to the Lambda runtime. This run function is actually going to start up the Lambda runtime. Behind the scenes, this is going to run a poller that's going to poll the internal Lambda runtime APIs, and then it's going to actually invoke your function. And then you just need to pass a function to this function that's then going to be called for each subsequent invoke. And almost every Lambda function you'd ever write would look the same as this. You're going to run that run function to start at the runtime, and then you're going to pass it something to be called for each subsequent invoke. What actually happens behind the scenes is that the Lambda service manages a set of pollers. So AWS is managing these on your behalf. You don't have to worry about these, and it's these pollers that are managing that interaction between Kafka and the Kafka topics and your Lambda function code. These pollers are going to pull that message from the topic, and they're going to invoke your function. When these messages get passed to your function, of course, that initialization phase is going to run if it needs to, and then the actual function handler is going to be called. These function handlers will almost always have a very similar structure. They'll always take at least one parameter, and that parameter is going to be the actual payload of the event that comes in. Now, Lambda functions are always invoked using a JSON string as the payload. But there's a really useful crate called AWS Lambda events, which gives you types for all the different types of things that Lambda might receive. So here you're receiving an event. It is a Lambda event of type Kafka event. If you were hooking this function up to, say, SQS, that would be SQS event. The runtime will then automatically deserialize that payload that comes in and allow you to work with an actual type, which is really useful. Notice you are then iterating over some stuff. The pollers will always invoke your Lambda function with a batch of messages. If you were to connect two topics to the same function, and then both them topics had multiple partitions, you would receive them as separate batches. So you'd get a top-level batch for the different topics, and then you get sub-vectors for the individual partitions. And then, of course, you need to go through and you need to process the messages that you've received. So your function handler code, when you process a message, is going to deserialize the individual message that comes into Lambda, and then it's going to call into your business logic. Now, when you look at these two things side by side, the one on the left being the one from your container runner, the one on the right being the code from Lambda, they're actually pretty similar. In your container image, you're simply calling the receive function to receive things from the Kafka topic. In Lambda, the poller's doing that on your behalf. And then you're deserializing the message, and you're calling into your business logic. Of course, in Lambda, you don't need to commit the message back to Kafka because the pollers are going to do that on your behalf, providing your function completes successfully. Because of the way you've structured your code base, it gives you this ability to move your code around. Your core business logic is captured in that core crate. That contains traits for your data access layers, maybe your actual data access code. And then the backend and web crates simply contain entry points, if you will, things that are handling the specifics about that specific way you're choosing to run your app. This is what would be known as the ports and adapters or hexagonal architecture style of building systems. So now if you want to switch to a different compute provider, you want to switch to a different adapter, you simply just need to add a different entry point. Deal with the specifics of that specific way you're choosing to run your code, and then just call into your business logic. It's this that gives you flexibility. It's this that helps you avoid vendor lock-in. So what you've ended up with here is actually a really powerful pattern in modern software systems. You've got a long-running container image handling web traffic, giving your users that really fast, really performant API. And then you've got some reactive style of compute spinning up and spinning down when there's work to be done. It's a really nice pattern. And the way you've built that gives you portability. Because of the way you've structured your code base and you've designed your application, portability has become a first-class citizen, which gives you the ability to move up and down that spectrum of compute options. As you maybe start to understand your workload better, maybe your team grows, maybe your CTO decides that you need to start doing platform engineering because platform engineering is cool, you can do that. Some of the best success stories I've heard in the serverless world are teams who've started off with serverless, and then as they've learned more about their applications, they've moved that application to run somewhere else. Keeping that in mind when you start building helps you consider doing that. But what about performance? We've got them horribly inefficient cold starts happening, right? How is that going to affect the performance of our applications? So here's the numbers of the application running on Fargate. This is the time taken to process an individual message. Remember, this is a container running with 512 megabytes of memory. When you port this application code to Lambda, you'll notice the performance doesn't really change at all. This has now got 128 megabytes of memory. So you're already using a fifth of the memory to process requests. Now, this is just the time taken to process the message, remember. What about those initializations, those cold starts? Surely they're going to really affect things. So when you generated these numbers, there were 850 invokes of your Lambda function. And the average initialization took 330 milliseconds. So the slowest message processing in your system was 732, the time taken to process the message, plus the initialization, which is about a second, which well, for a back-end system might be okay, but it's not ideal. What you realize when you look at this, though, is that out of them 850 invokes, only 3 of them were cold starts. Only 3 initializations happened. Only 3 requests got anywhere near that 1 second. The P50 was still 300 milliseconds. This is the big win now. You're starting to move towards sustainability. Even when all 3 of them environments are active, with 128 meg of memory each, you're still using less than your 512. And remember, this compute is only running when there is work there to be done. So this is becoming a bit of a win for sustainability now, right? You're starting to use resources only when they need to be used. But you think, what about this web app? You've still got a web app running 24 hours a day, 7 days a week. Sat there waiting to do stuff, even if there's nothing there to be done. Could this potentially move as well? And that's when you notice that this run function that the Lambda runtime uses, all that run function needs is something that conforms to the Tower service tray. And you also realize that the Eastham web framework is also built on top of Tower, which means your web API built with Eastham can actually run inside Lambda as it is. So in your startup code for your web app, you can simply check if the Lambda task root environment variable exists. This will only exist if the code is running inside Lambda, and if it is, run the application inside Lambda. Of course, if it isn't running inside Lambda, then you need to start up your API as normal. So how is that going to affect performance? Surely that's going to dramatically affect the performance of the API. You can probably see what's coming here. So these are the numbers for the API running on Fargate. The latency, the response time. Max response time, 420 milliseconds. Funny you think, when you run this web app in Lambda, the performance hasn't really degraded at all. Again, really all you've done is shifted the memory from 512 meg to 128 meg. So you're already using less resources, and you're only using them when there's work to be done. What about those cold starts? There were 1,350 invokes of your Lambda function over the time you ran this analysis. The average cold start time was 503 milliseconds. So the total max latency for your web app is just under a second, which isn't ideal, of course, but only 4 of them 1,350 invokes were cold starts. At scale, you start to see less and less cold starts. So now it can be really time to start to celebrate, because now you're building an application that's only using resources when there's work to be done. The application is still performant and it's safe. And it's now that you realize that you're never going to need to worry about accidentally turning off a server again. You're never going to need to worry about upgrading a Kubernetes cluster or doing any infrastructure things that, frankly, a lot of us don't enjoy doing. And you find yourself reflecting and thinking back to Oprah Winfrey. Oprah's a wonderful person, of course, but in this case, I'd say she's probably wrong, because it is possible to have all 3. And remember I said at the start, I'm pretty new to Rust. And I've been thinking about something Tim said in yesterday's keynote, that the Rust language is there to empower everyone to build reliable and efficient software. I'd actually argue that serverless gives you services that empowers everyone to deploy reliable and resilient software. It democratizes building reliable, scalable systems. Whether you are just starting out in a startup, you're building a hobby project, or you're building large-scale systems, serverless can help you build that. And maybe as you start to scale, as your team grows, maybe you do eventually choose to step out to Kubernetes once you understand your workflow better. But next time you're looking to deploy a Rust application into production, just consider serverless. See how that might help you. All the code samples for this talk are available on GitHub. As I said earlier, this is a real application. You can go and deploy it. And to kind of demonstrate this portability argument, you can actually run the exact same application on AWS, on GCP, on Azure, on Fly.io. There's various different services you can run this application. As a sneak preview, there's also an example in the repository using a fully serverless cache. So I added a cache to this as well, using a wonderful company called Memento, which changes the performance numbers to something like this. Consistent double-digit millisecond response times. So pretty cool. I'm also writing a book at the minute on Lambda functions and Rust. If you're interested in building with AWS specifically, you can get that on early access now. We've written about 6 chapters, so the book's now complete. You can get a discount because of that, and you can also get an additional discount because it is RustLab, so why not? And finally, thank you all very much for listening.